Využít mikrofon? Это распон. Поможет нам.
Is it okay now? Yeah, should be better. So we will be talking today about all things simplifying service provider transport networks. Segment routing, EVPN, and routed optical network. I think previous session also mentioned routed optical network in some sense, but I think this time it will be a little bit different. We are from Georgia, Georgian-based system integrator company, but we operate in 6 countries already for more than 20 years, and our main focus is on service provider networks like DWDM, MPLS, broadband, whatever. And we are Cisco Golden partners, Juniper Platinum partners, so we do a lot of different stuff, but mainly we are based on Cisco. But this presentation, disclaimer, it uses number of slides from Cisco Live openly accessible presentations and some slides from segmentrouting.net. They found from the inventor of segment routing, so not much by me, the slides itself. We'll be talking about NGN architectures, segment routing, EVPN, and then my colleague Levan will speak about DWDM, as he is DWDM expert with experience with both terrestrial and submarine DWDMs. So first of all, NGN architectures. So we need some core aggregation, access, service edge for these services, for services for other services like mobile and residential wireline. So let's speak about architectures a little bit. So, this part here is from 2012 presentation of one of the Cisco Live, and this design architecture was even earlier, I think 2005 or something, and it was talking about how important it is to put MPLS in between. When you have very big Ethernet network, you have to put MPLS in between to divide these Ethernet clouds into more manageable parts where VLAN significance, spanning tree, and this kind of things will be isolated by MPLS. And this design was evolving, and in 2014 it reached something called Evolved Programmable Network. It was very good design and very timely, because this is the time when service providers started deploying 4G and mobile traffic started growing dramatically, and much more cell-side routers were introduced in the network. So this concept was, it was answer to the scale limitation of previous designs when you have, say, 100, 200 routers in one IGP domain, and they run LDP and exchange labels there. So when you suddenly have 1,000 or 10,000 routers in your network, you need to somehow divide this. So BGP labeled unicast was introduced to handle this. So this was the history of designs, but at some point it also became limitation of growth factor for some countries, because they started seeing that subscriber bandwidth started to grow dramatically because of higher quality videos and YouTube and this sort of thing. So more bandwidth per subscriber, but subscribers are not willing to pay more money for the services. So service providers need to upgrade their network all the time, but are getting the same amount of money. Not too many things are constant in this life, but the fact that bandwidth is growing from all the time and nobody wants to pay more money for it, these two things are more or less constant all these years. So this is another slide from I think 2020 or so. And reading between the lines of previous slide, so traffic is growing, revenues are not growing, what should service providers do? And the vendors were pushing this paradigm that everything needs to be automated so that you can fire more engineers, keep less, pay them less, and deploy cheaper hardware. This was the time more or less when, let's say, Cisco SR9K and Juniper MX, they were switched to some Broadcom-based cheaper platforms, maybe even 10 times cheaper if you calculate dollar per gigabit. Modern transport platforms are much cheaper, but can do much less. So designing the networks with modern platforms became much more complicated, and there are much more caveats. So we will try to look into modern design. And it's not only Cisco, it's other major vendors are propagating more or less the same approach to make network automatable, manageable by centralized controllers, so that behavior of the network is more predictable. So what is the main thing here? To simplify the protocol stack which we have in current networks. So when I say current or future and so on, it depends on operator where it is in its life cycle. Like some operators already have done it, say, 4 or 5 years ago. Some operators have not even deployed BGP labeled unicast yet to get rid of single IGP domain. So it depends, every operator is unique and every business case is unique, but more or less the trend we are seeing is this. Current networks run LDP and RSVP-TE for label distribution. RSVP-TE for load balancing, but more so for fast reroute. Meaning protection. BGP labeled unicast for scaling interdomain, like when you have more than, say, 500 routers, you probably don't want to keep them in the same IGP domain because every link flap needs to be recalculated. So LSA advertised and Dijkstra algorithm run by all the routers in that area. So you need to somehow divide these things in reasonable size. Recommendations about the sizes are different. For me, it's about 100, 200. If you ask some vendor engineers, it can be 1,000, 2,000, but it depends also on stability of the links. If you have microwave, it's much less. If you have stable optical network with DWDM protection in place, then it's less of a concern. But still, it's BGP labeled unicast and the services on top of it. So we all know BGP L3 VPNs, it's our bread and butter, and for layer 2 services we use for pseudo wires and for VPLS, normally LDP, but maybe some BGP signaling, but most of the time it's LDP. So what this paradigm shift suggests is to replace all this transport stuff with segment routing, so one protocol to manage, one technology to master, and one controller which can oversee what's going on in transport domain, underlay, let's call it, and one protocol, BGP, to control all our services. So L3 VPN, it has been in place for many years already, but idea of EVPN introduction here is to replace LDP or whatever else, static and so on, with BGP-based control plane for layer 2 VPNs. So its analogy is like layer 3 VPNs are like dog. You can tame it, you can teach it something. Layer 2 VPNs are like cat. So it's very difficult to manage cat and make the cat to do whatever is required. So EVPN is, for the moment, best approach to it to make L2 VPN manageable. So we will be talking today, and also very important component here is DCO transceivers. So earlier or nowadays even we have DWDM departments in service provider networks and like MPLS departments, which sometimes work together, sometimes work against each other. I've seen any combination of it. And this brings new level of integration between these departments when you basically shift transponders from DWDM guys to routers. And they start managing these things together. And a number of protection, restoration stuff moves from DWDM to more flexible and intellectual segment routing layer. So now we will go into segment routing, but we will start from a little bit far. So segment routing is our foundation, this turtle on which the 3 elephants stand, and then all the stuff, the flat earth. So segment routing is foundation. And to understand what to do, how to get out of this trap that revenues are declining, bandwidth is growing, we need to go one step back to rethink what is this MPLS all about, why it happened, and what was the reason behind it. I know very well that the real reason for MPLS was its integration with IP integration with ATM, but ATM is dead. See, that's dead. But we will manipulate this history to make it more visible. So in the very beginning, we had this CSMA-CD, Ethernet things. Then we got back learning in our switches. And at some point, people decided that they need VLANs. VLANs inside the switch, so these red ports can talk to each other, blue ports can talk to each other, and they are more or less separated. Then we have 2 switches, so first floor, second floor, and we need this to achieve the same thing. So red should not talk to blue, and if we just continue this approach, we will need 2 cables from first floor to the second. That was cost prohibitive, and here came the idea of VLAN. What is VLAN tagging? So what is this tagging thing? It's when we put extra information on top of each and every packet to make this switch understand in which MAC address table to look up the final destination, in red one or blue one. So it's just adding extra label, tag, call it whatever, but it's extra piece of something to be transferred over the wire. Those of you who are old enough probably remember ISL. Nowadays we have .1Q. And this does it for local area networks very well. Now, VLAN was for layer 2, but there is layer 3, and VLAN for layer 3 is VRF, virtual routing table, virtual router inside the router, and we can have a lot of routers in one. Especially talking about service providers, we can have many customers, and each customer deserves their own routing table. So we have this number of routing tables, and we are facing the same problem. Should we use 3 cables to get from here to there for all these color VRFs? So not really cables, we already have .1Q tags, but initially this was called VRF Lite when we encapsulate each VRF in its own sub-interface. But then suddenly people come out with MPLS VPN label. So it's kind of a not really .1Q header, but something more sophisticated, which instructs this final router in which routing table to look up where to send the final traffic. Blue, orange, green, whatever. So it's taking idea of VLAN tagging one step further. Of course, here is one important piece missing. When I teach this class about MPLS, I use this analogy and students like it. Beer and vodka. So beer is service label, which decides which VRF the traffic should be looked up, and vodka is to decide to which egress PE to deliver this traffic. So normally we see two labels, service label and transport label. Of course, it gets much more complicated. With segment routing, we can have 10 or 12 or 15 labels. I've done myself just for lab purposes, but on some platforms, so platforms have generally this limitation how many labels can impose at one run of NPU, but well, on SR9 case Cisco, I've seen up to 12, I think. And even service labels can be, so normally in L3 VPN application, we see one service label, but EVPN can get wild and have two labels for various purposes. But the main thing is that beer and vodka, two separate substances, but when put together, they have much bigger blast radius. So service label, and it's also quite complicated with even with service labels within L3 VPN paradigm. You can have per CE label allocation, per VRF label allocation, and so on. So it has its own share of complications. But most importantly, what I wanted to highlight with all these historical excursions was that label is not just encapsulation kind of thing. It's instruction to the router what to do with the packet. So its label is instruction. Whatever this instruction means, look up in this VRF or remove label and send out of that interface or whatever. But let's remember that label is instruction. And we have, so in this picture, normally we see multi-protocol BGP distributing labels for L3 VPN, and a little bit later we will see multi-protocol BGP address family EVPN distributing label for layer 2 services. What about vodka part of it? Originally for transport underlay, people had to decide whether to invent new protocol for label distribution or to piggyback something to existing protocols and make them distribute this information. So originally, Cisco TDP, tag distribution protocol, it was called when Cisco invented precursor of MPLS called tag switching. They decided for whatever reason that it should be separate protocol. Nowadays we'll see that it could have been done differently because segment routing just extends ISIS and OSPF to distribute label information as well. So DP, if you, so it's used to be my favorite book, MPLS Fundamentals, describing all this LDP stuff. LDP is, if everything is fine, LDP works just fine, but as soon as it gets any problems, then it's absolutely wild to troubleshoot. It's very complicated. In fact, this is me thinking about this page in MPLS Fundamentals. What are the connection between bound addresses, routing table, label information base, and label forwarding information base, and what is preferred in which case. So LDP has a number of other drawbacks like LDP and IGP synchronization. You can have IGP session established, but LDP is not there yet, and you have to wait for something before you can start forwarding traffic, otherwise you'll get black hole, and so on. But that was plain vanilla MPLS VPN inside one IGP domain. Once it started growing, remember this 1,000 routers, 2,000 routers, 10,000 routers, we had to deploy recipe by Julius Caesar, divide and conquer. So we divide network in smaller IGP areas so that they are manageable size, but how do we get label information between areas? It's BGP labeled unicast. So BGP just gets another address family to also carry label information with it. And all of it works just fine, but it's very complex. It's not, this slide does not mean to scare you, but this is control plane flow, and this is data plane flow, push, pop, swap, gateway, and so on. So all of it is fine, but it's very difficult to automate, to get it under control of one artificial intelligence kind of a box, which will distribute traffic and create services automatically. So the dream of every management is that call center girl can click some things on this screen, and suddenly the new service will be created in the network, and the new channels will be added to satisfy it, and so on. So that's not possible without dramatic simplification of this stuff. So the step towards this simplification was invention of segment routing. What is segment routing? So what is this picture? It's map of Europe with roads built in Roman time. So Julius Caesar time roads, and we see that the road intersections are still, after 2000 years, this is Paris, this is Madrid, this is London. So for whatever reason, these Roman roads were designed so well that still now all the capitals in Europe, at least where the Roman Empire was present, are more or less on intersection of Roman roads. And this is the book by inventor of segment routing, Clarence Filch, Cisco guy. And it's absolutely fantastic book. It was, for me, its reading was like Treasure Island. So I could not stop, because he's not just giving technical details, but he's giving reasoning why and what was the reason, and how was this discussion with Deutsche Telekom and Sprint and whatever, what was the struggle with IETF, how it was born, this technology. And and he could have called it anything, but the game was that SR, segment routing, and Strada Romana, so Roman roads of Roman Empire. So he had this analogy, and he has even this picture of himself at Roman road in this book. What is this? What is segment routing? Segment routing is essentially source routing. When packet enters the service provider network, the edge router puts number of instructions to this packet frame, whatever service we are talking about. It puts on it number of instructions which determine the whole lifetime of this packet. So you go here, then you go there, then you go there, and then you exit network in that location. So the whole life of the packet is encoded in the very beginning at the precision level which is appropriate in this context. And we'll just see what I mean by that. So this is Zen Garden, Japanese stuff. But what these three stones here mean, it's label stack. So first instruction, second instruction, third instruction, and as the net packet goes through the network, these instructions are executed and removed so that packet reaches the final destination. So what is this segment? Segment is an instruction. And in fact, segment routing can be run on top of MPLS or can be run on top of IPv6. And in first case, it's every stone is MPLS label, and in case of SRv6, it's called, it's another inside IPv6 header. So we will not talk about IPv6 because it's not, as far as I know, it's not there yet, at least in my part of the world where we operate. I don't know of any SRv6 successful deployment yet, but probably it will come. But MPLS segment routing, there are a lot already, and we've done 3 or 4 already in Georgia, in Ukraine, in Belarus before the war. So what is segment routing? This is one analogy of what is the difference between segment routing and normal internet routing approach. So it's like capitalism and socialism. In socialism, you have planned economy and everything. So in capitalism, and internet, in fact, was designed for after nuclear war, so that let's say 80% of infrastructure is gone, and this 20% of infrastructure should still be able to somehow deliver at least some messages. So it was designed with survivability in mind, because it was product of military thing. So in this scenario, in internet routing, every router has its own routing table and decides by himself where to route this traffic. So every router is point of decision. So in capitalism also, every company operates on their own risk. With socialist economy, it was like some clever guy sitting in Moscow and saying that this guy should do this and I should do that. And we all know what happens to Soviet Union, fortunately. But but because it was not done properly, if it would have been done so that proper amount of decisions were taken centrally and proper amount of authority were transferred to local administrations, then it could have worked. Like in US, you have like president, and you have California and Texas, and whatever is good for Texas is not good for California, but overall stuff are managed by president. So this is where segment routing shines. This is proper balance between local intelligence and central management. So this idea is not new. So this is internet, and before internet we had telephone networks, we had frame relay, we had X25, which were inherently, so frame relay and X25 were inherently packet switched network, but ideology was like I signal a channel and then I send this traffic over this channel. So it was adaptation of circuit switching to packet switching. So not really paradigm change, but technology background was different. And in fact, RSVP traffic engineering does the same. RSVP traffic engineering also, so this is, we will see this slide one more time when we will talk about segment routing traffic engineering, but here I wanted here to show that segment routing takes into account from day one the fact that this is the packet switched network, and it can inherently use equal cost multipath or unequal cost multipath or whatever. So not just one way, but all the possible ways are used to reach from router 1 to router 3. If we want to, we can instruct it to use only this way or use only these 2 ways, but by default it will try to load balance across everything, unlike RSVP. So for RSVP, we can. Kavida. So time is passing much faster than. Okay, then I won't go into much detail, but this is probably the most important slide for today. 2 phases of segment routing. Philosophical approach of right balance between distributed intelligence and centralized optimization. So when there is someone who says that we need to produce this amount of cars and that amount of, I don't know, bread, and then each region or company or whatever does its best without instructions from the center. This is philosophical, and this is technical approach, the technical phase of segment routing, that it's set of labels to be put on top of customer traffic, no LDP, and these packets, we'll just see now the control plane and forwarding plane for it. Why segment routing took so quickly off? Because it absolutely reused MPLS forwarding plane. So nothing had to be changed inside the router, silicon or forwarding mechanisms, except the control plane, some extensions to ISIS or OSPF or BGP. Everything like push, pop, swap, whatever, all these operations remain the same. IPv6 is not that straightforward, so there are two flavors of IPv6, one big segments, small segments, and small segments is not supported by all hardware, but with MPLS, almost all modern router can do segment routing if you do software upgrade, and it's like every loopback gets assigned a special segment, and green segments, every link gets assigned a purple segment, and then you combine these segments, green and purple, and you encode the path. Like if I need to get from 1 to 5, first I want to get to 4 and then use this link for whatever reason. I encode 2 instructions. Remember the stones on this cover of the book. So this is first stone, second stone. Once the packet reaches router 4, this is removed, and it executes this purple instruction, forwarding traffic down to this link. And we get very easily to our beer vodka stuff, except vodka here is replaced by segment routing instead of LDP. And I don't get into details here, but segment routing can have their labels from IGP like ISIS or OSPF or BGP, including BGP egress peering engineering. For it, OSPF and ISIS had to be enriched with additional information. They propagate in the link stay advertisement. So this is the list of stuff for ISIS. One thing to know is that ISIS is much more so Cisco started doing segment routing initially and started working on both ISIS and OSPF. Other vendors decided to catch up and say that, okay, segment routing is the future a little bit later. So to get on the same level, they had much less time, so they concentrated on ISIS. So ISI compatibility and richness of features and so on is much better with ISIS. So if you have a choice, please go with ISIS on deploying segment routing. Although we've done with OSPF as well, and it works. And how do we migrate from one to another? We upgrade all the routers. So this is vanilla scenario when we have all the routers capable of running segment routing, and we upgrade them to proper software. We assign proper node seats, and one by one we just tell them don't. So we run SR and LDP in parallel. So for LFIB that's not a problem, and then at some point we just tell the router, this router, that router, does not matter in which order. When, say, IP packet comes in and it has to be encapsulated in MPLS in transport, should be SR or should be LDP. And so whenever we configure prefer segment routing, this gets fully segment routing, and this is still LDP, but still understands receiving segment routing encapsulated traffic is fine. And then you just remove LDP. So this is like marketing. Reality is a bit more complex. There are a number of things like mapping server for between LDP and SR, and number of the interworking solutions. And when you have like area where you cannot run segment routing, but you want to still run your L3 VPN, you still can do segment routing traffic engineering on the border for interest option B, or inline route reflectors for L3 VPN services. But yeah, this is what we do for living, our company, like migrating, performing complex migrations, and we have quite extensive experience with that. So, very first moment you deploy segment routing, you get immediately TI-LFA benefits. It's almost for free. It's like fast convergence, which was not achievable with IPFRR, remote LFA, RSVP traffic engineering can do this, but at much higher costs of suboptimal routing during restoration, and a lot of configuration required. I will not stop on these use cases. If you will need, you can. There are much better explanations of it on Cisco Live or wherever for TI-LFA. I'll just mention this one, non-obvious benefit of segment routing which we got. In a service provider network, we wanted to have accurate traffic matrix. Which traffic goes from CTA to CTB, and the country was like Ukraine, quite big, and we wanted to have traffic matrix. And we did a very simple thing. Sampled Netflow can export statistics about traffic per label stack. But with segment routing, it has different meaning, because for every label in transport stack, you know in your Excel file to which loopback, to which router does it belong. So reconstructing back all this information from sampled Netflow gave us almost very accurate traffic matrix, which could have been dived even deeper at service level, analyzing service labels. So it's our own development, and we even built what if analysis tool based on that. So it's another non-obvious thing. Another beautiful application of segment routing is Anycast pseudowires. Anycast pseudowire is when you static pseudowire with destination, and this destination lives not on one router but on two different routers, because segment routing can advertise same IP address with the same MPLS label, because it's under our strict control, from any number of places. So with truly Anycast. This Anycast has a number of applications, static pseudowire being just one of them. I will not get into traffic engineering probably to save time for DWDM, but please know that segment routing traffic engineering is really beautiful and much more comfortable with compared to RSVP traffic engineering, and gives number of benefits. So quickly switching to taming cats. Layer 2 stuff. So initially we had spanning tree, VLANs, and then Q in Q, VLAN stacking. Fortunately, I have not had any chance to work with this, because instead of IEEE, I went to IETF stuff. So Tahoma design was like VPLS, MPLS solution to this problem. So this is pure layer 2 solution to layer 2 problems. This is already MPLS solution to layer 2 problems, and it also had these iterations, VPLS, hierarchical VPLS, I don't know what it is. But finally, industry arrived to EVPN. EVPN is putting BGP on top of, so like what you call this, what you put on horse to make it right. So using BGP to make this cat tame. So VPLS could not do a number of things, like could not handle LACP dual homing because of traffic coming back, or a broadcast, if broadcast would arrive to this router and it would go to dual homed device, it would be duplicated, or this router would not learn properly from which router should this MAC come, because of say LACP on this router decides to send one flow here, one flow there. So it results on MAC flip-flop. So the solution was EVPN, which is, if you look at it, it's quite complex, but it's much like L3 VPNs brought down to one layer below. It has number of new paradigms, like EVI is same as VRF. Ethernet segment is like PAPC routing, but not really. And it had to use 5 or even more new BGP route types to make it all work for all use cases. This I have it printed out, put behind my monitor. I work with EVPN on daily basis, but I still have to look it up from time to time, all these EVPN route types. So EVPN, by the way, works on top of any MPLS and also on top of VXLAN. So MPLS and segment routing are not really necessary to make EVPN work. What are the use cases? Most easy one is dual homed pseudo wires, and beauty of it is that you have like pseudo wire from here to there, and then for whatever reason you take it to a different place, you do not need to reconfigure anything here. It's BGP based, and BGP will make sure that the pseudo wire is signaled to a different place. Many other benefits, but that's one nice thing. VPLS kind of thing, like with MAC learning, and every MAC address is redistributed in BGP as route type 2, and you can do hub, spoke, and play with route targets, or even more complicated hub and spoke enforcement topologies. Distributed layer 3 Anycast gateway, so remember the word Anycast, you can have, say, default gateway of this host, the same IP address here and there, doesn't matter, and they synchronize their ARP tables with each other. Otherwise, you cannot say, if this is LACP channel, you cannot do it without VRRP or other things, but here EVPN does it for us. We skip this one, and the last thing I want to show, especially interesting probably for residential broadband and this hierarchical L2, L3 service providers, is that there is this notion of flexible cross-connect. In one pseudo wire, you can have number of different VLANs, and so this is iOS XR syntax, but so this subinterface, this subinterface, this subinterface on access side, this is the EVPN magic, which brings it to the head-end router, see the same EVI target and so on, and then you can distill these things. So this can go to L3 interface, this can go to L3, so VRF, this can go to bridge domain, this can go to BNG subinterface and run whatever BNG, PPPoE, whatever you have. So even with CUPS control user plane separation architecture, it's the same pseudo wire head-end multiplied by flexible cross-connect. So EVPN powered stuff for building hierarchical services. Leon, I'm sorry I spent too much time talking about this.
I will take 10 minutes of your time. I want to talk to you about the routed optical networks. And the biggest driver of this technology is one of the biggest driver is the segment routing, which gives us an ability to move some parts of the properties and features from the DWDM network to the router. So, and the development of the digital coherent optics, which you see that back in the 2011 were the huge, and the in 2024 we have just the QSFP-DD modules, which compared to them use much less power and not power, and they have the much lower OSNR requirements and optical requirements as the previous models had. You see the traditional 3-layer control plane model. You see the DWDM layer, and it has the OTN layer on top and the IP MPLS layer on the top of that. So you have to have 2 or 3 departments that manage. One is managing the DWDM systems, and another is managing the IP MPLS systems. And you see that there are 3 levels of protections, and all the layers have to be precisely planned, designed, and developed and maintained. And who can track which span, which fiber cut can affect which link and which service, it is very hard. And also you have the very expensive DWDM transponder modules that requires much more investments than in routed optical networks. So you see the routed optical networks approach, where you have the DWDM optical line system, and you have the IP system on top of it. So the topology of the fiber optics and the IP router links are the same. So in this slide you see the traditional approach of the optical protection schemes. Some of them require twice as much transponders or optical components, or maybe colorless, contentionless, omnidirectional components in WDM systems, or they have some caveats in the PSM protection where you cannot use different lambdas there. In the IP protection scheme, you can it is more flexible, it is more predictable, but you have your engineers have to have more skill sets in DWDM than you had before. You see that you have the traditional approach on the top. You have the DWDM system separately, you have the routing system separately, and you have to connect them with the expensive client modules and transponders, and then transmit it with the DWDM system further. We can get rid of the most parts in the network and just use the QDD 400G or some kind of another IP over DWDM module that replaces the most expensive parts in our network. But we have to leave some kind of the ROADM or amplification optical line systems to amplify or add and drop some channels at some termination points. But we have another solution that we can get rid of the whole DWDM system, just inserting the EDFA amplifier, which is in the QDD little module, and it can amplify all our DWDM channels from in point-to-point systems. Another big advantage is that the modules, modern modules, QSFP, CFP2s or CFP-DDs are interoperable, and they can be used on the different vendors, between different vendors. So you can use the, for instance, Cisco module on the head end, and you can use the another vendor module in the tail end. And the roadmap of the modules, the most modern module is the CIM8, which can transmit 1.2 terabits per second in one channel, one lambda. And you can see the roadmap that it is planned to sell the 2.4 terabit module CIM10 in 2025 or 26. So disaggregation of the vendor-specific modules and brings us to disaggregation of the optical line system as well. So you have to transmit another vendor lambdas born on another vendor's modules. So you have to transmit the all types of circuits in your DWDM system. So we cannot be vendor specific today. One problem is that when you move some features from DWDM to the router part, you have to have the specialist engineers which can configure and which understand the optical configuration of these DCO modules. You see that you have to configure multiplexing mechanisms, you have to configure modulations, forward error corrections, and all of it is done already on the router. So you see the example of configuration 400G DCO module. You see that you have to configure bandwidth, frequency, you have to configure chromatic dispersion thresholds, and so on. You have to also troubleshoot these modules and all the errors you have in DWDM DCO module. So you have to, your MPLS engineers, you have to look into the optical parameters on your module as well. It is already done on some management platforms. So all the vendors have some hierarchical controllers, service orchestrations, and so on, and even open source monitoring system can show you the speeds, OSNRs, receive powers, and as well as the optical gains and total output powers from the DWDM optical system. So the conclusion is that you have the simpler DWDM networks. You have to you have the IP network integrated on the top of your fiber optical network. You have simpler designs. You have the advantages to use most of the modern silicon optics. You can transmit hundreds of gigabits per channel on point-to-point short links, and you can efficiently use the whole spectrum, and protection mechanisms are moved to the IP layer, which gives us ability to simplify the DWDM network. And Well, last but not least, you don't have the vendor log, and all of the modules understand the language with which it is configured on one or another vendor's router. That's it. I think it was